The removal of the depth requirement for ground ring electrodes and plate electrodes in the 2002 National Electrical Code, or NEC, was not a mistake. The requirement for a minimum depth of 2.5 feet for ground ring electrodes was deleted in the 1999 NEC. The requirement for a minimum depth of 6 feet for plate electrodes was deleted in the 2002 NEC. The substantiation for the deletion of the depth requirement for ground ring electrodes in the 1999 NEC stated that the depth of the ground ring electrode is not a factor in its effectiveness as a grounding electrode. The substantiation for the deletion of the depth requirement for plate electrodes in the 2002 NEC stated that the depth of the plate electrode is not a factor in its effectiveness as a grounding electrode, and that the requirement for a minimum depth of 6 feet was unnecessary and burdensome. The wording in section 250.53 that says where practicable rod, pipe, and plate electrode shall be embedded below permanent moisture level is intended to take the place of the depth requirement. This requirement is intended to ensure that the electrodes are in contact with moist soil, which is necessary for them to function properly. Now let's delve into the specifics of ground ring electrodes. A ground ring electrode is a big conductor that is buried in the earth, encircling a building or structure. It is used to provide a low impedance path to ground for electrical faults and lightning strikes. The size of the conductor used for a ground ring electrode is typically 2 AWG or larger. The conductor should be buried at a depth of at least 30 inches, or as close to that as possible. The earth surrounding the ground ring electrode should be free of rocks, debris, and other obstructions. The ground ring electrode should be connected to the building or structure's grounding system at multiple points. This can be done by connecting the ground ring electrode to the building's grounding electrode conductor, the metal frame of the building, or other suitable grounding points. The ground ring electrode should be tested periodically to ensure that it is providing a low impedance path to ground. This can be done by using a ground resistance tester. If the resistance of the ground ring electrode is too high, it may need to be replaced. Now let's discuss plate electrodes. A plate electrode is a metal plate that is buried in the earth. It is used to provide a low impedance path to ground for electrical faults and lightning strikes. The plate should be made of a conductive material such as copper or galvanized steel. The size of the plate should be at least 2 square feet. The plate should be buried at a depth where permanent moisture is expected. The earth surrounding the plate electrode should be free of rocks, debris, and other obstructions. The plate electrode should be connected to the building or structure's grounding system. This can be done by connecting the plate electrode to the building's grounding electrode conductor, the metal frame of the building, or other suitable grounding points. The plate electrode should be tested periodically to ensure that it is providing a low impedance path to ground. This can be done by using a ground resistance tester. If the resistance of the plate electrode is too high, it may need to be replaced. Now let's discuss the importance of embedding electrodes below the permanent moisture level. The permanent moisture level is the depth in the earth where the soil is always moist. This level varies depending on the location and the type of soil. It is important to embed electrodes below the permanent moisture level because the moisture in the soil helps to conduct electricity. This ensures that the electrodes are providing a low impedance path to ground. If the electrodes are not embedded below the permanent moisture level, they may not be able to provide a low impedance path to ground, especially during dry periods. This can increase the risk of electrical shock and damage to equipment. To determine the permanent moisture level, you can consult with a local soil expert or refer to local building codes. In general, the permanent moisture level is typically at least 2.5 feet below the surface of the earth. When installing electrodes, it is important to take into account the permanent moisture level. If the electrodes cannot be embedded below the permanent moisture level, you may need to consider using other types of grounding electrodes such as ground rods or ground rings. Ground rods are metal rods that are driven into the earth. They are typically made of copper or galvanized steel. Ground rings, as mentioned earlier, are bare conductors that are buried in the earth, encircling a building or structure. Both ground rods and ground rings can be used in situations where it is not possible to embed electrodes below the permanent moisture level. The NEC provides specific requirements for the installation of grounding electrodes. These requirements are intended to ensure that the electrodes are installed safely and effectively. It is important to consult the NEC before installing any grounding electrodes. Now let's talk about section 250.53 in more detail. This section of the NEC covers the installation of grounding electrodes. It states that where practicable, rod, pipe, and plate electrodes shall be embedded below permanent moisture level. The phrase "where practicable" means that this requirement is not always mandatory. In some cases, it may not be possible to embed electrodes below the permanent moisture level due to site conditions or other factors. However, the NEC encourages installers to embed electrodes below the permanent moisture level whenever possible. This will help to ensure that the electrodes are providing a low impedance path to ground. If it is not possible to embed electrodes below the permanent moisture level, the NEC provides alternative methods for grounding. These methods include the use of ground rods, ground rings, and other types of grounding electrodes. It is important to choose the appropriate grounding method based on the specific site conditions and the requirements of the NEC. In addition to embedding electrodes below the permanent moisture level, the NEC also requires that electrodes be installed in a way that protects them from damage. This can be done by installing the electrodes in a protected location, such as inside a building or in a concrete enclosure. The electrode should also be protected from corrosion. This can be done by using electrodes made of corrosion-resistant materials, such as copper or stainless steel. The NEC also requires that the connections to the electrodes be made with corrosion-resistant connectors. This will help to prevent the connections from corroding and failing over time. Proper grounding is essential for electrical safety. It helps to protect people from electrical shock and to prevent damage to equipment. By following the requirements of the NEC, you can ensure that your grounding system is safe and effective. In summary, the removal of the depth requirement for ground ring electrodes and plate electrodes in the NEC was not a mistake. The substantiation for these changes stated that the depth of the electrodes is not a factor in their effectiveness as grounding electrodes. The NEC now requires that electrodes be embedded below the permanent moisture level where practicable. This requirement is intended to ensure that the electrodes are in contact with moist soil, which is necessary for them to function properly. When installing grounding electrodes, it is important to consult the NEC and to follow all applicable requirements. This will help to ensure that your grounding system is safe and effective. Now, consider some additional details regarding ground resistance and testing. While the NEC doesn't specify a maximum ground resistance value for single electrodes, it's generally accepted that a resistance of 25 ohms or less is desirable. If a single electrode doesn't achieve this value, the NEC section 250.56 mandates the installation of an additional electrode. The two electrodes should be spaced at least 6 feet apart. This spacing helps to ensure that they are in contact with different areas of the earth, which can improve the overall grounding system performance. Ground resistance testing is typically performed using a 3-point fall of potential test. This test involves driving 2 ground stakes into the earth at specific distances from the electrode being tested. A ground resistance tester is then used to measure the resistance between the electrode and the ground stakes. The fall of potential test is a reliable way to determine the resistance of a grounding electrode. It's important to note that ground resistance can vary depending on soil conditions, moisture content, and other factors. Therefore, it's recommended to perform ground resistance testing periodically to ensure that the grounding system is still functioning properly. In addition to ground resistance testing, visual inspections of grounding electrodes and connections are also important. These inspections can help to identify any signs of corrosion, damage, or loose connections. Any issues that are identified should be addressed promptly to ensure the continued effectiveness of the grounding system. Let's also consider the role of the grounding electrode conductor. The grounding electrode conductor connects the grounding electrode to the building's main grounding busbar or neutral busbar. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. NEC Table 250.66 provides guidance on selecting the appropriate size of the grounding electrode conductor. It is important to use a grounding electrode conductor that is large enough to safely carry fault current. An undersized grounding electrode conductor can overheat and potentially cause a fire. The grounding electrode conductor should be installed in a protected manner. It should be protected from physical damage and corrosion. The grounding electrode conductor should also be installed in a way that minimizes the risk of ground loops. Ground loops can occur when there are multiple paths to ground, which can create unwanted circulating currents. To minimize the risk of ground loops, the grounding electrode conductor should be run directly to the grounding electrode without any unnecessary bends or splices. Now let's discuss some common misconceptions about grounding. One common misconception is that grounding is the same as bonding. Grounding and bonding are both important for electrical safety, but they serve different purposes. Grounding provides a path for fault current to flow back to the source, which allows the overcurrent protection device to trip and de-energize the circuit. Bonding, on the other hand, connects all metal parts of an electrical system together to create a low impedance path for fault current. This helps to prevent voltage differences between metal parts, which can reduce the risk of electrical shock. Another common misconception is that grounding is only necessary for electrical equipment. Grounding is also important for other metal structures such as fences, pipelines, and storage tanks. Grounding these structures can help to protect them from lightning strikes and other electrical hazards. In addition to the NEC, other standards and regulations may also apply to grounding systems. These standards and regulations may vary depending on the location and the type of facility. It's important to consult with a qualified electrical engineer or inspector to ensure that your grounding system meets all applicable requirements. Finally, let's consider some best practices for grounding system design and installation. Firstly, design the grounding system early in the project. This will help to ensure that the grounding system is properly integrated with the overall electrical system. Secondly, use high-quality grounding materials and components. This will help to ensure that the grounding system is durable and reliable. Thirdly, install the grounding system according to the NEC and other applicable standards. Fourthly, inspect and test the grounding system regularly. This will help to identify any potential problems and ensure that the grounding system is functioning properly. By following these best practices, you can help to ensure that your grounding system is safe, effective, and compliant with all applicable requirements. The grounding system is a critical component of any electrical system. Proper grounding is essential for electrical safety and equipment protection. By understanding the principles of grounding and following the requirements of the NEC, you can help to ensure that your grounding system is safe and effective. Remember that local codes and regulations may have additional requirements or variations on the NEC standards. It's always best to consult with a licensed electrical contractor or local electrical inspector to ensure compliance with all applicable codes and regulations in your specific area. For example, in some jurisdictions, the minimum size of the grounding electrode conductor may be larger than what is specified in NEC Table 250.66. Or, there may be specific requirements for the type of grounding electrodes that can be used in certain soil conditions. Therefore, it's crucial to verify local requirements before designing and installing any grounding system. Furthermore, technology and best practices in grounding are constantly evolving. New materials, methods, and equipment are being developed all the time. Staying up to date with the latest advancements in grounding can help you to improve the performance and reliability of your electrical systems. Consider attending industry conferences, reading trade publications, and participating in online forums to stay informed about the latest developments in grounding technology. Also, remember that this information is intended for educational purposes only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or licensed electrical contractor before designing, installing, or modifying any electrical system. Electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others from electrical hazards. Ensure that all work is performed by qualified individuals who are properly trained and equipped to handle electrical tasks safely. Consider the specific application when designing a grounding system. For example, the grounding requirements for a hospital or data center will be different from the grounding requirements for a residential dwelling. Critical facilities require robust grounding systems to ensure uninterrupted power and protect sensitive equipment from damage. The NEC provides additional guidance for grounding sensitive electronic equipment in Chapter 6, Article 647, Sensitive Electronic Equipment. The type of soil can also affect the design of a grounding system. Soil resistivity is a measure of how well the soil conducts electricity. Soils with high resistivity require more extensive grounding systems to achieve a low impedance path to ground. Soil testing can be used to determine the soil resistivity at a particular site. This information can be used to design a grounding system that is appropriate for the specific soil conditions. The presence of underground utilities can also affect the design of a grounding system. It's important to locate all underground utilities before installing any grounding electrodes. Contacting underground utilities can be dangerous and can disrupt service to other customers. Call 811 before you dig to have underground utilities located and marked. Furthermore, remember that grounding is not a one-time task. Grounding systems require periodic maintenance and inspection to ensure that they are functioning properly. Schedule regular inspections of your grounding system to identify any potential problems before they become serious. Repair or replace any damaged or corroded components immediately. Keep records of all grounding system inspections and maintenance activities. This information can be helpful for troubleshooting problems and for planning future maintenance. By following these guidelines, you can ensure that your grounding system provides reliable protection for your electrical system and equipment.